Okay, so today we will be planning to learn more application of first order linear differential equation. So last time we learned how we can computationally find the solution approximation. Okay, so one of the simplest model, and we will derive a model here for this law. So in future, suppose somebody gives you certain hypothesis and they ask you to set up a differential equation out of it. So it would be a good exercise here how we will proceed. Okay, so it states that rate of change of temperature of an object is proportional to the difference in temperature between the environment and the object. Okay. So change in temperature. So we have to stick with some notation here. So first of all, when we are given any problem like a law and we want to derive a model, we have to convert it into a mathematical format. Right now it's just a word problem. Okay, so so here notations we can take as Ts to be as temperature of surrounding. Then what else do we need? We need temperature of an object at a time t. So temperature of object at time t I will denote as capital TT. Okay, so what else do we need further? Initial temperature. Now we start applying this law. Okay, so rate of change of temperature. So how do we write rate of change of temperature? What is the mathematical expression for rate of change of temperature? What do you think it will be? How will I express rate of change of temperature in these notations? Temperature is capital T. It depends on little time t. So it will be d capital T divided by dt, right? So this is rate of change of temperature. And what this law is saying is proportional to the difference in temperature between the environment and the object. So well, proportional, we still have to formulate this. What does this mean? Proportional to the difference in the temperature. Now you can say that it could be capital TT minus TS, or you can say it could be TS minus capital TT. It can be either way, the difference. But if something is, say, losing the temperature, it's getting cooled down, so its temperature originally will be lower or higher.
So initial temperature?
Right.
Will be higher. If it's cooling down?
If it's cooling down. The initial temperature will be higher, and then it will keep losing the heat to the surrounding, right? So Ts, if it's cooling down, then what can you say about Ts and TT relationship? Ts will be, if it's cooling down, is it less than TT or greater than TT? It won't cool down if its surrounding is at a larger temperature, right? It has to be at a lower temperature. Then it will start cooling down. Okay, so I will say here Tt minus Ts, and the reason I kept it like this, because in order to remove this proportionality constant, I will introduce a constant here, right? So I will say that dTt over dt is nothing but constant times Tt minus Ts. Now as you can see, this has to be positive, so k has to be negative, but to further impose k is positive, I will introduce a negative sign in the front. Okay. So now the decay in temperature is taking place, and here assumption is k is we are taking as positive. Okay, so now we have this differential equation. We want to solve this. This is modeling this law, but and with the initial condition T0. You can just leave it as T0. No need of further denoting it with something else. Okay, so how we will solve this? Is it a separable differential equation? Ts is constant, it's fixed. We are assuming that, because I mean it's of such a big, so right now the outside temperature is, I guess, 43, 42 degrees Celsius, or in Fahrenheit 3 degrees. It's too hard. Anyways, so now you are suppose sitting in an air conditioned room, and then you came out of that room. So your temperature might be 23 if you are inside. If you come out, it's not affecting the outside temperature at all, right? Even if you now experiencing hot, it's not that the outside temperature gets again randomly changed to 20 something. I mean, if that happens, it's amazing. So, but it doesn't changing. So outside temperature is not depending on the time. Now we want to solve this T of an object, how it's changing. So this is a constant. Now what you will say, is it a separable differential equation or not? You have to solve this for capital T. Capital T is an unknown function here. So is it separable? K is constant, unknown function is capital T. Okay, let me help you. Let me simplify it further. I'll denote let yt is equals to capital Tt minus Ts, if this helps further. So then your left hand side will become d of yt plus Ts, right? Because Tt, if you simplify this for Tt, it will be yt plus Ts. So if I place it back up here, then it is derivative of yt plus Ts divided by dt. Okay, and my right hand side is minus k times yt. Now, sum of two function differentiation, how will you do that? You differentiate. How will you differentiate this with respect to time? What's the derivative of this whole thing? Anyone?
So if yt equals tt minus ts, and you move the ts to the other side,
Right.
how is yt on the right side? Like you just put minus k times yt.
So if you add Ts both the sides,
Yeah.
you get Tt, right?
Yes.
So that means Tt is nothing but yt plus Ts. Okay. Now Tt minus Ts is yt.
Yeah.
So again replace this side also with y. Okay. So basically convert this whole thing in terms of y, because the reason I did it, because it's very familiar notation for you. Y function is unknown. Now, how will you differentiate this left hand side? What's the outcome from here? Ts is constant because I said it will not change.
Y prime t is just fine.
Just y prime t, right? Y prime t. Okay, now is it separable differential equation? Yeah, this is a familiar notation, right? So this is separable, and what is the solution for this differential equation? I think by this time you are, without computation, you can tell what is the solution. C e to the power minus k t, where C is initial condition. At time t equals to 0, what is y0? At time t equals to 0, y0 is equals to t0 minus ts. So I will replace this constant, which is nothing but your c. I will replace this c by this expression, and I will further replace y with this, because I eventually want capital T, t. Okay, so I am replacing here y with tt minus ts. I am replacing this constant with initial condition t0 minus ts and e to the power minus kt. So the temperature of an object at time t will be equals to Ts, surrounding temperature, plus T0 minus Ts times e to the power minus kt. So this is a formula of how temperature of an object will change as time changes. Surrounding temperature will be given to you in the problem. Initial temperature will be given to you in the problem. Maybe sometimes you have to find this proportionality constant k, but this is the key which you will be using for Newton's law of cooling. Okay, so let's do an example then. So is it clear to everyone how we derive this temperature T? Any question in any step? I just replaced y with whatever I have defined before, and I plugged the value of this constant because y0 is c. K times 0 0, e to the power 0 1, y0 is c. So y0 is t0 minus ts, so c is t0 minus ts, and everything stays in the formula. Okay. So if you have any question in the derivation, you can ask right now. Okay, no question. Let's move then. Let's do an example. Body cools in moving air according to Newton's law of cooling. Assuming temperature of air is 0 degree, find the proportionality constant K if temperature falls from 40 to 30 degree in 200 seconds. Okay, so what is Ts? 0 degree. Now we need to use that formula. So what is initial temperature here? Hmm? 40. Final temperature 30 degree, because we are trying to find proportionality constant, and at 200 seconds, in 200 seconds it reaches to 30 degrees Celsius. So this information we have, and let's plug all these terms back in the formula up. So t at 200 is 30, ts is 0, t0 is 40, ts is again 0, e to the power minus k times, this is t, which is 200. So I will get here e to the power minus 200k is equals to 30 over 40. Over 4, and then you can further simplify this value of k, which will be nothing but, you can either write down as 1 over 200 ln of 4 over 3. I changed the sign here, that's how I got rid of sign minus here, because k eventually have to be positive the way we set up this model. If I don't introduce a negative sign initially, then my k here will be negative in order to make it positive. Okay, so it's up to you, and I think this is always good that if we assume all constant positive and introduce the sign as per the law, so that we eventually will be looking for positive value rather than negative value. Okay, so this is there. Now the second part, find the time for the difference in the temperature to fall from 30 to 20. So 30 to 20 and k we already have it here. We need to find time now. So final temperature will be 20, initial temperature will be 30, surrounding temperature remains the same, and k we will use this value. So now I will show you one important trick, and it should be an observation as well when you are solving the problems by yourself later on. You should make use of that. Okay, so let's plug this value. So we will have 20 is equals to 0 plus t0 is 30 minus 0 e to the power minus k times t. Now k we already know from here, but as you can see, if you explicitly compute this k in this expression and then plug it here, you will be introducing an error in the time t, because it would be round off in some sense. Okay, what we should do in order to be more accurate is we should not plug k here, rather we should multiply by 200 and divide by 200. Now this is a computational, when you are doing something computationally, these kind of small tricks helps you to avoid round off error in your approximation or in your code, whatever final thing you are looking for. So now this is like here you are having this trick, but this is kind of like a thinking you should develop, that when you are trying every step, when you are trying to write a computational program, are you incorporating round of error at every step? And if you are, eventually you are incorporating a lot of round of error. So your thinking should be somehow try to keep the fractions, try to make it free from decimal points. Okay, so now coming here, e to the power minus 200k, we now know e to the power minus 200k is 3/4. So I will not simplify it, and I will just place 3/4 right up here. 20 divided by 30 is equals to 3/4, and 3/4 will have a power, right, because this is a power of exponential, to the power t over 200. So far till this step we have not incorporated any error. 2/3 will come here, 3/4 to the power t over 200. you can take ln both the sides. And then you simplify this expression for t. So you will get here t over 200 is nothing but ln of 2/3 divided by ln of 3/4, which will be nothing but ln of a divided by ln of b is what? So I can write what here? ln of what? So, okay, so ln of a over b or ln of a over ln of b, which one is equals to ln of a minus ln of b?
Isn't it ln a over ln b? I don't remember the actual trade still.
I will not proceed any further if I don't get a correct answer. How many of you are voting for top one and how many of, okay, let's start. Bottom one, how many of you? Hey, come on. Bottom one. Which one is true? This one or this one? I want answers from this side as well. Top one? Okay, figure it out. If I get the same answer from everyone, then it would make sense. Now you have to figure it out. Okay. So, but you will see here, if you have placed the value of k and tried to compute t, you will get some number. And if you keep marching like this and then try to compute t, you would have more accuracy. Okay. Let me tell you one thing.
What's the top one? What's the top? Was cheating not allowed? Because I don't know if we're going to figure it out.
You figure it out. I'm still, some said top, some said bottom. Bottom was lower, top was also there. You figure it out. Okay, so mixing problem. The best way to figure out something is use some values and try to see if you have difficulty in figuring out. Okay, mixing problem. It's also one of the application, and I would say an important application of first order linear differential equations. Okay, I was listening this talk yesterday, and there was a guy who was explaining how high school kids couldn't take mathematics properly. I would say, I mean, his point was for high school, but I would say that was also not just for high school, but for even higher level classes as well. Seeing a problem, what do you see first when you see a word problem? First thing, what flashes you in that problem? Bunch of units, and basically what, to be honest, you would be looking for is formula. What's a formula where I can feed in all these bunch of values and that's it? Math is not like that, to be honest. And I would say it's very bad in terms of a textbook, how they are designing, that you have all the mathematical structure and every single thing. If I would have not given you anything in this problem, and I have kept two beakers here, one is containing salt and another is containing pure water, and I start pouring a salt in the pure water and started creating a problem out of it, at what time the concentration will be this thing, then we will look for a notations to set up a mathematical structure for that word problem, and you should create this problem by yourself. That is the best way of learning math and seeing how, given a physical situation, what you really need, what are the parameters you need, then how will you trying to create a formula out of it, setting up a differential equation and then solving it. Not like seeing any word problem. Forget about, like, now at this level, when you see a word problem, don't just look for a formula and I will feed in all these numbers and that's it, I'm done. Take some time initially of the lecture and the starting of the course, and then at times think like, okay, this is my physical situation, maybe the person cooked up this problem like this, now these are the terms and I have to fit a model and then like this. Just a way of thinking. Okay, so let's proceed now in this problem. Unfortunately, we have the full problem. We are not posing it like a physical situation and then doing it. If I do that, it will take me one till whole session just creating one problem and solving it. But I'm just telling to you that you should think when you are on your own, you should think like that for a problem. Okay, so coming back here, you have a tank. So I will not even think about anything given here. I will just draw a tank. I want to see a tank, how it looks like. Okay. And somewhere there would be, it's initially full of pure water. And its whole capacity is 2 meter cube volume. At time t equals to 0, salt water with salt concentration 5 grams per liter begins to flow into a tank at the rate 10 liters per minute. Now somebody comes and they start pouring here salt water. You might see another terminology in textbook, brine. Brine is also another name for salt water. So they start putting a salt water in this pure water tank, and the rate at which it is entering begins to flow at a rate of 10 liter per minute. Okay. Well mixed solution in the tank is pumped out at the same rate, and the same rate we are taking out also the solution, because you don't want it to start overflowing, so it's going inside and you're taking outside also. So they are asking you to set up an initial value problem for the amount of salt in the tank at a time t minutes. So basically you should forget every single thing and just focus on this last line, amount of salt in the tank at time t minutes. So what is the unknown function in the whole problem? Because if we want to set up a model, we have to look for an unknown function. Unknown function, I would say here, is amount of salt at time t, because that's what we are trying to find eventually. So amount of salt in tank at time t minutes. Okay. So we need to set up a differential equation for this unknown function so that we can monitor what time, how much salt is there within this whole tank. Okay. So rate of change of amount of salt will depend on what?
T over T.
Yeah, that will depend on, this should be equals to what? Salt is changing it within inside the tank. It will depend on the rate by which we are putting the salt inside, and the by rate we are putting it out, taking it outside, difference of that would be remaining inside. Right? So that makes sense. So if something is going inside and going outside, whatever is the difference will be inside, left inside. So it should be rate in minus rate out. That would be rate of change of the amount within inside the tank. Okay, and initially the amount of salt, what was the initial amount of salt within this whole tank? 0, because it was pure water. Very good. Okay, so A0 is 0. There is no salt, it was pure water. Okay, now we need to understand what are the units for rate. If I consider here, I can see this moment amount. What will be the unit of amount? If I go back up here, grams I would say would be unit of amount. Okay, if grams is a unit of amount, then rate of change unit will be gram per second, because we are taking over dt. So if we want this rate in as gram per second, we need to make use of, we need to get those same units. So as we can see, it is saying that salt concentration 5 gram per liter begins to flow into the tank at rate of 10 liter per minute. So it should be how much will be rate in. So okay, so it should not confuse you like that. It is rate at which it is flowing. But yeah, I should erase this line here. It should not confuse this to be the, because we have to stick with the units. So 5 times what you will say, dA over dt should be rate in, I want grams per liter times something liter per second, so that it will be consistent with the outside unit. Okay, and grams per liter, how much was it? 5, and flowing with the rate 10 liter per second. Now this is rate in. Huh?
It's 10 per minute. So
Is a minute?
67.
Okay, minutes. Okay, let's keep it in then in minutes. So eventually then it overall will be in time and in minutes. So let's put it in minutes then.
So liters cancel.
I mean, yeah, then we will take units of time to minutes then in that case overall. Okay, so now what is rate out? We know it is flowing by 10 liters per minute again, out also. But what is this amount here? What do you think? Should I place when we are taking it out, the salt? Water. Because we don't know at that particular time what is the amount of salt in it. We know the whole tank is filled with pure water, which is 2 meter cube. So we can take here, and if we convert into liters unit, then it should be amount at that time of that salt divided by the volume. Okay? And that would give us the whole setup of the model. AT divided by volume, and I think I should keep consistent with the notation 2000 liter. It was 2 meters cube and 2000 liters, right? So keeping all this up here, we have set up now the initial value problem of basically modeling a mixing problem. and setting up an initial value problem for that. Okay, so this is the initial value problem. Now part A is done. Part B, we have to solve this problem, and let's go up. It is asking find the time when salt concentration in the tank becomes 4 grams per liter. Okay, so it's asking the time when it will be 4 grams per liter. Okay, let's first find amount and then we will see further. So is it a separable differential equation? $50 minus $80 divided by 2000, and 110 is also there, so 200, and then you have A0 is equals to 0. So is it a separable differential equation? How do you separate it? You should have a derivative should be equals to function of that times function of time. Now I think you can simplify it. 200, if you make a common denominator, it will be 1000 minus 80 divided by 200. So you can then treat this whole thing and take it in a denominator and dt on the right hand side, and you can separate this easily. So it is separable. You can also see that this is a linear problem. It's a linear differential equation, first order. So you can apply integrating factor technique as well. So both the things you can do with this. Okay, so let's, which one you want to do? Let's do integrating factor, because it's very simplified form here. So dA over dt is equals to, so you convert into standard form, which is 80 over 200 is equals to 50. So your IF, integrating factor, or another terminology I am using here is UT, is equals to e to the power integral 1 over 200 dt. Right? So this is the integrating factor, and now we will multiply throughout with this integrating factor. We will get here e to the power 1 over 200 t times a prime t plus e to the power 1 over 200 t at over 200 is equals to 50 times e to the power 1 over 200 t, or t over 200, I can write it down. At any rate, this is left hand side is nothing but derivative of at times e to the power t over 200, and right hand side you have 5 e to the power t over 200. Integrate both the sides. If you integrate both the sides, you will get 80 e to the power t over 200 is nothing but integration of this is you get this in a denominator, but it is 1 over 200, so it will come in the numerator and make it 1000 e to the power t over 200 plus a constant of integration. Okay, so you will then divide entire expression by e to the power t over 200, and you will get 80 to be as 1000, and then c times e to the power minus t over 200. So you get this. This is amount of salt in the tank at time t. Since A0 is 0, that means what will be the value of C? C has to be negative 1000. So okay, so AT turns out to be then 1000 minus 1000 e to the power negative t over 200, and this is I am here applying A0 is equals to 0 and getting the value of C. Okay, so this is the amount of salt at time t. And what is the second part asking us? Give the time t such that salt concentration in the tank becomes 4 gram per liter. So now they are saying concentration, and concentration has unit grams per liter, but what we obtained is grams, right? Amount is in grams. So if I divide the entire expression by the volume, then I will convert AT over the volume is concentration, and then I will look for, equate it with 4 and look for time t. So that's an idea. Okay, so we have got here amount. Now we want 4 concentration, 4 grams per liter. So what should I divide with AT with? What do you say? 2000. 1000 divided by 2000. Now this whole thing, since we are dividing by 2000, we are dividing throughout by 2000 because we don't want to change the expression. E to the power minus t over 200. Now this whole thing is 4. If this whole thing is 4, what is AT then? 8000. So if you plug 8000 here and then simplify the equation for time t, you will get the time when the concentration is 4 grams per liter. Okay. So so you want me to do it, or you can do it? So AT has to be 8000, and if we plug 8000 up here, we will able to get the time. So 8000 and you are dividing, so it's 8 is equals to 1 minus e to the power minus t over 200. So this will imply e to the power minus t over 200 is equals to negative, which doesn't looks right. Negative 7, right? It is giving exponential function can never take a value of negative. So where is the problem? Oh, how did I get to 5 when there is a 50 here? So miss this, here should be 50. So that means, where is the change then?
10,000 is not 0.
So we are integrating with the side, so it should be 10,000, right? And then our C will be again negative . Right, so you have 1000 coming up. Okay, so here you have this, c will get multiplied. You should have 0 up here. Then you are doing a, 0 is 0, so it would be 10,000. So it should be this, right? Then what is the difference here? 8,000 will remain like that, but if I am dividing by 1000, there is a 10 here, and I have here also 10, right? Okay, now this makes sense, because now we are not getting negative value, because exponential function cannot be negative. So I thought, where did we missed something in calculation, and what we missed is we didn't carry that 1 0, and that's the reason we end up in that negative value. So now coming back up here, 8 is equals to 10 minus 10 times this, so that means this will imply 10 e to the power minus t over 200 is equals to 2, because 8 minus 10 is negative 2, negative negative will get cancelled and you have this. So e to the power negative t over 200 is 1/5, and then you can just do ln. Ln of 1/5, or other way round, so this will imply t is equals to, so 5 over 1, so ln of 5 times 200. And this is in minutes. So sometimes when you are doing calculation, you might also can make the same error which I made here, and then you can see, oh, there is now something wrong, because my exponential function can never be negative. We went back and we figured it out, it should be 50 instead of 5. Okay, so this is how you will solve for time, and you have to be very careful in units in this example. Okay, so then now let's see how much material is left in this week 2 session. So I do have one problem which I want to give it to you. By the way, before closing today's lecture, there are two things which I want to say. One thing is, in your homework, you will be finding a hard time if you are trying to integrate first in the homework 2. First order linear differential equation, you will have a hard time in integrating. But if I give you this hint, it will be much easier for you. That what is the integration of 1 over, I think those who were there in my previous class, they will be knowing this, but 1 over x ln of x. Can anybody, like, I want everybody to do this integration for me in class today. 1 over x ln of x dx integration. It's not tough, you can do it.